All right, class. The next topic is looking at new functions from old functions and the idea of a transformation. This is section 1.3. We looked at the concept of mathematical models, okay, and various types of functions, such as linear functions, polynomial functions, rational functions, algebraic functions, exponential functions. And we also looked at a lot of properties, logarithmic properties that I hope you practice them to be comfortable to move on, okay, class? So let's take it from there, and we're gonna move on to the new stuff. All right, so logarithmic functions, exponential functions, and the graphs we are comfortable with. So we are looking at new functions from old functions, which is really the idea of a translation. And first, we're going to quickly remind you of vertical and horizontal shifts or translations. To make life easy, we assume C is positive. If you look at the graph, it shows you what's happening. First, the vertical translation, basically, f of x plus c, that means if you have the function f of x, it shifts up by c units, and f of x minus c shifts down by c units. In the case of f of x minus c, it shifts to the right by c units. We are assuming c is positive, class, okay, to make this easier to understand. And if it's f of x plus c, it shifts to the left by c units. I hope you remember this from basic algebra that you had, and again, college algebra, pre-calculus. So some basic transformation you're expected to be comfortable. Okay, so translation along the x-axis, translation or transformation, or the shift, okay, any other along the y-axis. Then we have this compression, okay, stretch and reflection, okay. So the idea is that if you are given y equals f of x, and again, c specifically, we choose it to be larger than 1. If you put that in front of a function, it multiplies the y by that, okay? If it's 1 over that, it shrinks it by that much. But what happens when you put it inside f of c of x, it has the reverse effect along the horizontal direction, okay? It's a shrinkage along the horizontal direction, and if it's x over c, it stretches. And to understand that, the best way is to look at sinusoidal functions. We'll do that, and we'll see how it works. If you have a negative sign, you want to treat it separately. For example, instead of negative, you have -5, then you look at 5 and then negative. The negative in front of f will flip over the function, okay, when it comes to the x-axis, but if you put it inside, in front of x, it flips over with respect to the y-axis. So those are the shapes that are going to happen. And again, I hope everybody remembers those. I don't expect you to do a lot of transformations, but some basic transformations I expect you to remember. Okay, class? So I hope it's clear. So these are the transformations. Again, as far as c being larger than 1, we are looking at compressions, stretches, and reflections. Okay. Let's look at this example. Okay, the function is given as y equals 2 cosine x, okay? And we want to start with cosine x. So going from cosine x to 2 cosine x, 2 is in front of cosine x, so the y coordinate gets larger by 2. For the same x coordinate, it is the y coordinate that gets larger by 2. So take a look at this graph. If you have a number in front of your function cosine, okay, it's very straightforward, or any other function. You just keep the same x's, the y coordinate is changing, and whatever number is in front of it. For example, 2 or 1/2. 1/2 makes it smaller, 2 makes it larger. It's not a big deal. What I want to make sure we understand is this part. And I want to explain this one to you by looking at y equals cosine x, where t is equal to 2 pi. Okay, so t equals 2 pi, meaning you go from 0 to 2 pi. So pay attention to this one, okay, all the way to, those are important parts, all the way to the end, okay, that is supposed to be 2 pi, okay. This number is 2 pi, class. 2 pi is almost 6.28, okay? 6.28. But what happens to the other functions? So let's use a different color. So when you're looking at y equals 2x, okay? Now t is 2 pi divided by 2, which is pi. I hope everybody remembers that, okay? If you have a number in front of it, it will affect your period. So the period is pi. So therefore, now you go from here to here. Let me see what color I want to use to represent that. See, look at this graph now. So a whole function, I'm looking at one period, class. Of course, it can go indefinitely on both sides. So I want you to see this one now, the yellow one, if you. The period has changed from 2 pi to pi, okay? And the green one, let me use it. For this one, t is 2 pi divided by 1/2. So it's 4 pi. And that's why this is a portion of that. Let me see what color I can use to show you here the graph that is, the graph in green, but I want to show you with a different color. See, this one, okay, this continues, okay, beyond that. So this will look something like that, okay, class? So the period originally is 2 pi. When you're dealing with cosine 2x, it's cut in half because 2 pi divided by 2. And when you're dealing with cosine of 1/2 x, then it stretches, okay? So the best way to understand this is looking at the sinusoidal function and looking at the period and the effect that it has. So I hope this is making sense. Now, the next question is asking for the transformation starting with y equals square root of x. So what I expect you to know is that the graph of y equals square root of x looks something like that. Obviously, this is to scale, but if you draw it roughly close and it's not to scale, it's not important. As far as I'm concerned, I want to know that you know the general shape. Doesn't have to be perfect. So we have that. Okay, so that sounds good. Okay, everybody's happy with that. Now let's do the transformation by looking at part B. Part B says, okay, we want to look at y equals square root of x minus 2. That means look at the given graph. We always go back to that original graph, part A. Now, we are going to look at that, and all we have to do, shift it down by 2 units. So shift down by 2 units, okay? So we're going to shift it down by 2 units. So it will look like this. As a result, 0, 0 goes to negative 2. 0, 0 changes to 0, negative 2. Location of 0, 0. So what matters is when you're graphing this, you want to always show important parts. For example, you can see what happens to the y-intercept. Remember, we had x and y-intercept, both of them at 0, 0 originally. Originally, 0, 0 here, okay? Now 0, 0 changes to 0, negative 2. You can also calculate this location. How? You replace the y with 0, and you calculate it, and that becomes 4, and you can see the location is 4, 0. Again, I just want to show you one of them. You can calculate the rest of them accordingly. So I hope that one is clear. If you look at the next one, now this is shifted along the x-axis, and that is 2 units to the right. So your 0, 0 is now at 2, 0, okay? And really the reason it happens, in order for square root of x minus 2 having the same y coordinate, remember the idea of this one, in order to have the same y coordinate as this one, you have to replace this x by x plus 2. That's why it shifts to the right class. Now x plus 2, and then minus 2, that gives us x, and it becomes square root of x. So to get to the same y coordinate, then you have to add 2 to x. That's the idea, okay, in case. The next one says, okay, what about y equals negative square root of x? Well, you're gonna flip that over with respect to the x-axis. And so what happens is, it looks like that your intercept remains intact. Okay, so you flip it over, okay, and that's what you get. Okay. Now, how about y equals 2 square root of x? When we look at 2 square root of x, the y coordinate is being multiplied by 2. So it stretches by a factor of 2. For the same x coordinate, the y coordinates are larger by a factor of 2. Just for the sake of argument, if x is 0, you still have 0, 0. But if x is 1, now 2 times square root of 1. That's what happens. And finally, if you have y equals square root of minus x, it is important not to think square root of minus x. Minus x means negative. That's not what it means. It means the opposite of x, okay? And so with respect to that concept, x is being changed to negative x. It flips over, this time with respect to the y-axis. This time with respect to the y-axis. So you have the same 0, 0, if you will, as your intercept, and you can find the values. For the sake of argument, the domain has changed from 0 to infinity now to negative infinity to 0. Okay, so for example, if you choose x to be negative 1, then y becomes positive. All right, so we have that. Absolute value, okay, it was discussed before. Again, I'm refreshing your memory as far as the meaning of an absolute value. Absolute value remains intact in general if it's positive or zero. Otherwise is the opposite. Again, if you go back to the basic definition of an absolute value, which represents distance from zero, and we looked at absolute value of A before, okay? So it's the same thing here. So again, recall, we said absolute value of A is A. If A is larger than or equal to zero, and it's negative A, is A less than zero. Now, what I want you to really understand is, when we say negative A, it doesn't mean a negative value, it means the opposite of A. That's the meaning of that, everyone. Okay, the opposite. Okay. So, how do we graph the absolute value function? There are two parts to it, or there are maybe a bunch of parts. The part that is above the x-axis remains intact, nothing changes. The part below, however, will flip over. So here's what's going to happen. We're going to look at the very first simple example. Everybody knows how the graph of f of x equals x squared looks like. And then with minus 25, it shifts down by 25. So take a look at f of x equals x squared minus 25. So x squared, and then shift it down by 25 units. This is the graph. Everybody is happy. Not a big deal, class. Now, the portion in blue is above the x-axis. The portion in blue remains unchanged. Okay, I notice sometimes things stay blurry when we move things along. So again, the portion in blue above the x-axis remains unchanged. The portion below is in yellow. It will flip over with respect to the x-axis. So look at the graph. This is how the graph is going to look like. So how do we graph an absolute value function? Depends which portion is above, which portion is below the x-axis. Okay, everybody? All right. So what happens to absolute value of square root of x minus 1? As always, let's start with step by step, start with absolute square root of x. So we know how the graph looks like. Again, whether it's to scale or not, I personally don't care. So we're going to do step by step. So y equals square root of x is graph. The next one, we are going to graph inside the absolute value, which is square root of x minus 1. That means it shifts down by 1 unit. So step 1, the basic elementary essential function of y equals square root of x. Step 2, shift it down by 1 unit. Now, step 3, let's go with an absolute value. Okay, which portion is above the x-axis? So notice this portion is above, so this is not going to change, everybody. Fine, so you can graph it just the way it is. However, this portion is below. It will flip over with respect to the x-axis. That's all there is to it. Notice what happens. The yellow one just flips over, and therefore your y-intercept that was 0, -1 changes to 0, positive. That's it. So I hope it's clear. So simple transformations like this, I expect you to be able to do something that simple. Okay, class? All right. What else is happening in this section? We are looking at algebra functions. If you recall, algebra functions in short represent the operations. If you recall, we had operations on numbers. Now we have operations on functions. So when we say the sum function f plus g of x, simply put, it means f of x plus g of x. The difference function would be f minus g means f of x minus g of x. F g means f times g. F over g means f of x over g of x. Okay. Now, what happens is to understand, how to do the operation is very simple. But as far as the domain, if A represents the domain for f and g, for g is b, it is always their intersection, which is the answer. A intersection b, whatever is in common. The only one that you want to be more careful is the last one called the quotient function. In the case of the quotient function, obviously you can divide by 0. So not only it's the intersection of the two, g can't be 0. By the way, as far as the notation is concerned, this looks like an epsilon and it's read an element of, this is in set theory. So x is an element of A intersection B, the one that looks almost like an N. It is the intersection class. So A intersection B, that would be the domain for all of them. For the last one, because we are looking at f of x over g of x, g cannot be 0. So we want to be very careful of that. All right, so let's move on to the next example, class. We are given f of x equals square root of x and g of x equals square root of 2 minus x. The first one, very obvious. We've seen it. We've seen the graph. It's an essential function. We know the domain x is larger than or equal to 0, and that means from 0 to infinity. For g of x, anytime you have a root function, when the index is even, it doesn't matter it's 2 or any other number that is even, then you set that larger than or equal to 0 and you solve. If it's odd, there is no restriction. So 2 minus x is larger than or equal to 0, okay? And you can solve, okay? So x becomes less than or equal to 2. From here, you should see that x is less than or equal to 2. Anyways, so in this case, from negative infinity to 2. Now, if we happen to have the following functions, f plus g of x and f over g of x, we want to see their domain. Okay, let's see if we can figure this out. Remember what we did. We found the domain for each piece. Okay. Now, what is the answer? A intersection B. Now, in part C, A intersection B. So, what is the intersection of these two? Okay. The intersection goes from 0 to 2. Okay. If it helps, you can graph this one, class. This is 0 to infinity. That would be the answer for this point. Now for part B, and I'm going to use a different color, and I'm going to use the same set. Negative infinity to 2. If this is number 1 and this is number 2, that means from here all the way to negative infinity, right? So what's in common? It's this portion, 0 to 2. Now, f over g, or f plus g, or f minus g, or f times g, they have the same, basically the same answer. The only restriction is that g, okay, this can't be 0. So what makes this 0? 2, therefore 2 is out. So your domain is a little bit more restricted. It's a little bit more restricted. Therefore, number 2 is not included. Number 2 is not included. I hope everybody is following what happened. The only thing is the restriction on the denominator. Okay. The next thing is the composite function. Everybody remembers f of x, g of x, f of g, and g of f. And by the way, they are not the same. Okay. You put the x into the g machine, g into the f machine, and it spits out f of g. If you put f and then g, it becomes g of f. F of g and g of f are not the same in general. So what is true about them? They become equal if they are inverse functions. Now, what is their domain? So I want to discuss that quickly. It's very simple to figure out what the domain of f of g is. By definition, f of g means f of g of x class, right? So first you look at g of x. Whatever is not going to go for g of x is excluded, because g of x itself is the domain of f. So whatever makes g of x undefined is out class. And then you look at the final result. You finish the job, you look at f of g of x, and then see if there's anything else that needs to be excluded. It's fairly straightforward. All right. Here's the easy example. We have f of x equals x squared and g of x equals x minus 3. We want to find their composite function. Obviously, they are not the same. F of g means this. Replace the x with x minus 3. And you end up with x minus 3.3. You don't even have to square it. That's good enough for needless to say, if you want to, it's x squared minus 6x. Plus 9, okay, if you want to change that. Now, g of f, on the other hand, is g of f of x. Okay, so replace the x with x squared, and the answer is simply x squared minus 3. It's very straightforward. Composite functions. You have a few more pages, class, it's not a lot. If f of x is given, g of x is given, h of x is given, can we find f of g o h? Okay. You can find them in any order. You can find f of g, then f of g of h, or you can find g o h and then f of that. Anyways, it's fine. There are really different ways of approaching that. F o g by definition is f of g of x. So you replace the x with x squared. And now you replace the x with h, which is x cubed plus 16, this f of g. Do you have to square it and simplify it? You don't have to. Is this the only way? No. You can find GOH first, class. I highly recommend you try this on your own. First try GOH and then FOG. That's absolutely fine. The point being, there's no one way to handle this. Now, when it comes to finding F and G where FOG is given, it may not be a unique answer, but it is only done by inspection, class. I can't emphasize this enough. So we want to find two functions. We want to find f of x and g of x such that their composite function becomes square root of x plus 2 over square root of x. Now, it's not unique, but some are easier than the other, okay? So this is the composite function. If you choose f of x to be x plus 2 over x and g of x to be square root of x, I hope you see, of course, you have to show that. This is not a finished job. You have to show that this works, okay? F of g must be what we have. I suggest you do that on your own. I also suggest try see if you can find other functions than what we have here to give us the composite function. We have a couple more pages. It shouldn't take long class. All right. I'm not going to dwell on this. I'm going to show you a couple of them, and the rest of them you can do on your own. They're very straightforward. Use the given graphs to come up with the answer. So f of g of 2, okay, by definition is f of g of 2, you need to calculate g of 2. So what is the g of 2? And remember, the g function is the blue function, okay? So what is g of 2? So we locate this point. Let me use a different color. We locate this point. And this point has coordinates what? 2 and 5. So that means g of 2 is 5. Okay. Now, what are we looking for? F of g of 2, that means we are looking for f of a 5. So 1, 2, 3, 4, 5 gives us here, look at this point. What are the coordinates here? The coordinates are 5, 4. So the answer is 4. This is what you need to do for all of this. That's why I don't want it to take too much time. This is very straightforward. And the answer becomes 4. G of f of 0, okay. F of 0 is 0, so you want g of 0, which becomes 3. F of g of 0, okay. F of g of 0, you have to find g of 0, g is the blue one, which is 3, and then f of 3, which is 0. So I hope you see it's very straightforward. You guys can find the rest of them. The only thing I want to explain in case it comes up, what is g of f of 6? It's g of f of 6, okay? And so the f function is the red one, you find it to be 6, and g of 6 is not defined, it's not given. You can find the rest of them. I'm not going to, spend any more time on that. Please take your time to make sure you're comfortable with those. I want to look at the next page, and there are 2 more pages. At the very least, we get something started for the next page. We're going to finish it, and the following maybe at least half of it. I highly recommend you have the questions and the answers. You check it, make sure you can find them. All right. Here's a graph, okay. And the graph of f of x is given. Draw the graph of the following functions. Again, if it gets complicated, I don't expect you to worry about that, but just the concept, I want to make sure is understood. By that, I mean, how would you graph something this simple? You just pick up a couple of points. If you can, and of course you need more than that, but if you can figure out 2 points, you have the rest of it. So just to be on the safe side, I have picked up the points. So pick a couple of pairs. Here's an example. Negative 2, 2. Take a look at negative 2, 2. Okay. This is negative 2. Okay. See. And the other one is 1, 3. And there are more, of course. See where they go with the transformation. Okay. So if you look at those 2, when we say f of x minus 3, that means the y coordinate, okay, is shifted by how many 3? So you write the same x coordinate and you subtract 3 from the y coordinate. Do you see that, everybody? So for part A, your x coordinate is not changing. Your y coordinate is changing by how many? 3. It's going to go down by 3. So the first one, 2 minus 3, and the second one, 3 minus 3. And you can do the rest. You see the graph, class. You need a couple more points, but as long as you can do 2 points, you can do the rest of it. What happens to part B? F of x plus 1, okay? That means we are shifting the graph 1 unit to the left. That's the meaning of it, okay? So let's see what happens in that case. So if you're shifting the graph to the left, that means you're not changing the y coordinate. So if you look at those two pairs, the y coordinates stay intact. The x coordinates subtract 1. So the first one is -2, subtract 1 becomes -3. The second one, the x coordinate is 1. So this one, class, is the first one. Subtract 1. This one is the second one, subtract 1, and you have those pairs, and here's the graph. Again, this is not to scale, but I hope you get the picture. In this case, part C, y equals 1/2 f of x. That means for the same x coordinate, the y coordinate gets multiplied by 1/2. Okay, so if you look at the first pair, -2, 2, -2 doesn't change, but 2 gets multiplied by 1/2, or half of that, which is 1. The next one is 1, 3. 1 remains intact. 3 becomes 3 divided by 2, or 3/2. So those are the pairs. Here's the graph. For part D, x doesn't change, but negative is in front of f, and the y gets multiplied by -1. Okay, so the first pair, -2, 2 changes to -2, -2. The second one, 1, 3 becomes 1, -3. And there you have your graph. Okay. Let me quickly go over the last page also. It's worth looking at it, class. Just 2 more minutes. Okay, let's look at the last page. It's worth it. Okay. Again, in order to understand how it's done, I'm just looking at a couple of pairs. Okay, one of them is 0, 1. Okay, so this is 0, 1. And another one is 1, 2. Those are the ones we have, and I would go with 2 more. If I'm graphing, I need more. But if you can do 1 or 2, that's good enough. So for example, y equals f of 2x, okay? The meaning of 2x is shrinking the graph, okay, horizontally by a factor of 2, okay? So what it means is that your y coordinate stays intact. So 0, 1, the 1 remains the same. 0 gets divided by 2, which is the same thing. But for 1, 2, 2 remains the same, and 1 divided by 2 is 1/2. So the x coordinate is being divided by 2. And you do the same thing for a couple more. You have the graph. I've given you more pairs, okay? Now, what about part B? The x is intact, but the y, okay, is changed. My apologies. The y is intact. The x is now the 1/2. That means really the reverse process. Okay, so we stretch it horizontally. So those numbers get multiplied by 2. So the first one is 0, 1. 0 doesn't change, but the second one is 1, 2, and the 1 gets multiplied by 2. And there you have it. Okay. Now, finally, we are looking at part C and D. So part C, f of minus x. That means for the same y coordinate, x is changing to minus. So 0 changes to -0, which means nothing. It's the same thing. So 0, 1 stays the same. But 1 and 2, 1 changes to -1. Okay. Finally, minus f of minus x. So not only x changes, also the y changes. Okay, that's the idea. So now the y changes also. And again, you really need a couple more pairs. You can graph it accordingly.